Hello, this is Dr. Oz. Today I would like to talk about nonlinear optimization problems. Before this video, we talk about other types of optimization models, started with linear programming, and then we moved into integer linear programming. And in this video, I would like to talk about the nonlinear programming. Okay, so nonlinear programs are optimization models. At least one of these should be nonlinear, either objective function or at least one of the constraints. So when I say nonlinear, what do I mean by that? So this is nonlinear, right? X cubical nonlinear, x to power 4 nonlinear, ln x is nonlinear, sinus or cosinus of x is nonlinear, 1 over x is nonlinear, and so on. And linear functions, if you remember from our previous videos, basically they are y equals to mx plus b, right? They have coefficient and they have y-intercept, but the power, the secret here is the power is 1. All right, now I'm going to talk about a little more uglier functions. So to do that, I would like to introduce an example, par inc, and I will first talk about unconstrained problem, and then I will talk about the constrained version of that problem and solve the problem. And we will talk about the shadow price analysis in this nonlinear program. So let's say in this problem, the par inc decided to move into market for medium to high price golf bags, and their distributor agreed to buy all the golf bags from them next 3 months. Okay, that's a good news. So in this problem, I would like to first define the decision variables. And from your economics 101, you guys probably remember, if you have taken economics, that there's an inverse relationship in general between price and demand. So the higher the price is, lower the quantity demanded or sold. The lower the price is, the higher the quantity sold. All right. So let's define our decision variables. I would like to decide, this is more like a marketing problem. Decide the price of standard bags and price of deluxe bags. So this is the price of standard bags and the price of the deluxe bags. Okay, so these are my decision variables I'm trying to decide. And obviously these decisions will change the quantities that will impact, right? All right, so let's move on to the next slide. And here you can see that marketing study, you need to do marketing study, by the way, to get this relationship in real life, a market study. And probably you will use some kind of regression analysis or some kind of relationship that will be found by some analytical model. So probably regression. So here let's define S and D. These are the quantities sold or demanded for standard bags and deluxe bags. Quantity sold or demanded for regular standard bags is based on this relationship, 2,250 minus 15 P sub S, which means that if I increase the price of standard bag by $1, I expect to have 15 units of less standard bag demanded. Let's do the same thing for the deluxe bags. This is 1500 minus 5 times P sub D. All right, every dollar deluxe bag increase basically will decrease my quantity demanded by 5 units. Again, these are, we got to be careful about these, because let's say if I have price of 1,000, that will give me this area right here, 15,000. That doesn't make any sense because number will be negative. So that's why this kind of analysis is true within certain price range. All right, so let's move on. cost to produce a standard bag is $70, and cost to produce a deluxe bag is $150. Okay, we have cost information here too. But so far, I don't see anything nonlinear, right? So let's introduce profit. Excuse me. Again, probably you need to do some kind of regression analysis here to understand the relationship between demand and the profit contribution. And let's say this is your relationship. The more I have demand for standard bags, more profit I generate until certain limit, because I have S square term here with negative coefficient. A similar situation you see with the deluxe bags. All right. And these kind of functions are called quadratic functions, because the power is basically 2. All right. So let's go to the next slide. And here I would like to talk about some graphical representation of this problem. So those, let's say I have some constraints in this problem, and these constraints are represented with these dark blue. Let me just highlight them with my red ink. These lines, and I have a certain number of hours available or resource available for me. So based on that, everything under these lines are feasible. However, everything out of those lines are called infeasible. So why do I want to have an infeasible solution? Because nonlinear programs are more complicated to solve, and in general we start with a infeasible solution and try to move towards this direction into the feasible region. Again, maybe the move is not that straight, maybe zigzag, 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 zigzag. We just try different solutions until we find feasible solution. All right, so let's move on. So if I solve this problem, unconstrained problem, if I don't have any constraint, and if I just plug in these values into my this objective function profit, and try to maximize this using Excel solver, which I will show you how, you will get the best solution over here. Again, I will show you this value. So what do I see here is the best solution is selling 600 regular bags or standard bags and selling 375 deluxe bags, which you will end up with profit of 52,125. Okay, so what is this? So this is an infeasible solution, obviously. However, this is a great upper bound for my solution. Upper with double P, not triple. Upper bound for my solution. All right. So this is the best you can achieve, but this is infeasible, so you cannot beat this. So this gives you some kind of indication how much maximum you can generate out of this. All right. So if you introduce the constraints to this problem, now I need to calculate the cutting and dyeing, sewing, finishing, inspection, packaging hours. Okay, so let me just write down the objective function for you here. So my model is maximization problem. I'm trying to maximize 80 S, which is demanded for standard bags, minus 1/15 S square, plus 150 D, the demand for deluxe bags, minus 1/5 D square. And subject to, again, my decision variables are S and D here. And subject to the constraints that I have here for the department. So I have cutting department, constraint, sewing department, constraint, finishing department, constraint, and finally I have inspection department, constraint. And I have 630 hours here available. Sewing department, I have 600 hours available, 708 hours available excuse me, in finishing department, and 135 hours available in inspection departments. And these constraints are less than or equal to constraints. So I cannot spend more time than those hours. And again, you need to have some kind of time study to get these time consumptions to produce these bags. So it looks like every standard bag takes 7/10 of an hour. Every deluxe bag requires 1 hour of cutting department. And every standard bag requires half an hour of sewing department and 5/6 hours of sewing department is demanded per unit of deluxe bags. Every standard bags requires 1 hour of finishing department, and every deluxe bag requires 2/3 hours of 40 minutes of finishing department. Finally, every standard bag will require 1/10 hours of inspection department, and every deluxe bag will require 1/4 or 15 minutes of inspection time. So, and also I have non-negativity constraints here. S and D demands should be greater than or equal to 0, obviously, because I cannot really have a negative number of demand. So again, this is my objective, which is a nonlinear function, and these are my constraints right here, and these are linear functions. So since I have at least one nonlinear function, this is called nonlinear optimization model. So let's look at the graphical representation of this problem. Again, we say that we start with the unconstrained solution, which is right here, $52,125 of objective profit. And if you remember linear programming, our contour lines for objective function was linear. But as you see here, these are not linear lines anymore. These are like ellipses. And you can see this is a mountain. This is the peak of the mountain, and you go down and down. So if you go to the next layer here, you will see that this will give me exact same objective function. But still, if you look at this one right here, this ellipse, there is no feasible point on that nonlinear line. If I expand that to the second ellipse here, you will see that only this point right here is intersecting with my feasible region. So that means that it's the feasible solution, which is also the best solution because that's the ellipse that's closest to my starting infeasible point of objective function. Perfect. But if I just keep moving this way, basically I will start having more feasible solutions right here. However, those are suboptimal because this point right here will give me the profit of $49,920.55. But if I go counter of more bigger, basically I'm going downhill from the mountain, my profit would decrease. So why would I do that, right? So this is my optimal solution. And to be able to reach that point, you'll use Excel solver, but I want you to understand the intuition. Basically, Excel solver will use an algorithm that will take a bunch of derivatives, which will improve the objective function the fastest in this way. And since this is a function that is I will talk about this more, that is like this shape, right? The peak point is 1, and then when you go this way or this way, the value goes down, monotonous, right? So this is easier to solve. However, once you have multiple mountains, you may end up with a point where for this maximization problem, this optimum solution, where right here you can start here and it will go up and up and up. So you may find this solution, but that may not be the global optimum. Let me just talk about those a little bit in my next slides. So I will show this in my next video using Excel solver to find the best solution. But before that, let me just talk about how Excel does those derivatives. We call that as Lagrangian multiplier. Basically, Excel will calculate the shadow price for me for a constraint, that all the constraint that I have, and it will try to find the rate of change, which is derivative of the objective function respect to that constraint right hand side, and whichever direction giving me the best solution, immediate step, Excel will move into that direction. All right. So if I do this by Excel, which I will show you how in Excel, you will get the best immediate moving position for cutting and dyeing department, and because of the shadow price of 26.72, which is gonna be your shadow price, which will increase your profit. So okay. So it's important to understand allow increase and decrease limits too, but I will talk about those in my Excel solver sensitivity analysis. It may not make sense at this moment much, but once we see solver solution, I'm pretty sure this will make more sense. Actually, I would like to talk about local and global optimal solution again. We talked briefly about that. So let's dive into that. So local optimum, again, a feasible solution where no other feasible solutions with better objective function in immediate neighborhood. Immediate neighborhood. So maximum of that is gonna be local maximum, minimum of that will be local minimum. But our goal in general in optimization is finding global optimum, basically overall what's the best solution. So that's it for this video, and next video I will solve this power problem using Excel solver and talk about sensitivity report. And until next video, enjoy business analytics.